Hello, everyone. So last time we were looking at numerical methods and Euler method, which was a numerical method to find estimation for solutions of a differential equation. Basically, we wanted to know if we have a solution of a differential equation, then what would be the estimation of that solution evaluated at some arbitrary point. And that method was specifically helpful if we have equation that it's hard to solve it or hard to find the exact solution, or maybe even impossible to find the exact solution. In that case, it would be very helpful to apply this method and to have at least estimation for our solutions. Now today I want to move on to the next topic, which is 1.8, exact solutions, exact equations. So consider a first order ODE. We are still in the topic of first order ODEs. First order ODE of the form, let's say m of x and y plus n of x and y times dy to dx equals 0, where m of x and y and n of x and y are functions of two variables. In general, we are assuming that they're functions of two variables. Of course, in particular cases or special cases, they could be functions of one variable, but in general, we can assume that they're functions of two variables. Then now we want to know under which circumstances the solution of this differential equation is a function of the form f of x and y equals c. So the goal is to find conditions such that the solution of ODE above is of the form capital F of x and y equals c. And this is, of course, we know that this is an implicit equation. F of x and y equals c is an implicit equation, because in math 113, as I said previously, in math 113, you learned that if you have y equals a function of x, then it's called explicit equation. But if there you have a mixture of x and y, for example, x plus xy plus e to the y, for example, equals 5, then that would be called implicit equation. So we want to consider this arbitrary form of implicit equation. We want this to be the solution of this. We want to know under which circumstances, under which condition, what type of condition should we put on m and n, so that this equation has a solution of this form. And of course, we want to find the solution as well. Moreover, we want to find the solution under the assumptions that we are going to derive. We haven't found the assumptions yet. What type of assumptions do we need on m and n so that this equation has a solution of this form? We don't know it yet, But once we find out that assumption or those assumptions, then we want to know under those assumptions, how can we find the solution of such a differential equation? Now we want this guy to be the solution of our equation. So let's start to derive the assumptions or to derive the conditions. Let's start with this equation, f of x and y equals c. Then I'm going to differentiate both sides with respect to x. Differentiate respect to x. Then I'll get, d to dx of capital F of x and y equals d to dx of c, which is 0. Of course, derivative of a constant function is 0. That's we know for sure. But how can you find derivative of capital F of x and y? Capital F of x and y is a function of two variables. How can you find the derivative respect to x? So this is, we need a fact from Math 213. Maybe you haven't taken Math 213 yet. In that case, I'm going to explain briefly what we need here. So if let's say z equals f of x and y, a function of two variables, and assume that, let's say, x is equal to x of t and y is equal to y of t, then we can find dz to dt using the chain rule, using the multivariable chain rule. Via dz to dt will be equal to df to dx, dx to dt, plus df to dy, dy to dt. So this means partial derivative respect to x. This is notation for partial derivative respect to x. And this is notation for partial derivative respect to y. So let me explain it about this. So here t is an independent variable, and we have x and y both dependent on t. So we have one independent variable, which is t, which could be time, and x and y both depend on t. So you can imagine, for example, let's say a rectangle. Let's say if this is, these are the length and width of the rectangle. You can assume that both width and length increase as time passes. So t is the independent variable, x depends on that, y depends on that. And if you look at, for example, area of the rectangle, that's x times y. So as time passes, x increases and y increases. So x can be written as a function of time, y can be written as a function of time. Area itself is a function of x and y, it's x times y. But it can also be written as function of time only. Because x can be written as a function of time, according to my assumption, x can be written as a function of time, y can be written as a function of time only. So if I substitute these two back into my equation, I will have z as a function of time only. So originally z is a function of x and y, but each x and y, each of them can be written as a function of time only. So if I substitute back, z can be written as a function of time only. So I can talk about dz to dt because z can be viewed as a function of t only. And how can I find dz to dt? This is a multivariable chain rule formula. We don't want to prove it. Of course, it has proof, but we don't want to prove it. It says dz to dt is same as df to dx, partial derivative with respect to x times dx to dt, plus df to dy times dy to dt. So these are the notations. These are curly. These because, you know, I'm meaning partial derivatives because f is a function of two variables. So I need the notation for partial derivative. But this is dx to dt. It's just a standard d because x is a function of one variable only. So this is not a typo. X is a function of one variable only. So that's why we use standard d. But this is f is a function of two variables. So we need the notation for partial derivative. We need to specify whether we are differentiating respect to x or respect to y. Let me give an example of this. So for example, let's say let f of x and y, let's say let z equals f of x and y equals x squared plus xy. And let x equals t squared, y equals t cubed. Find dz to dt. So see, z is a function of x and y originally, but x itself is a function of t, y itself is a function of t. So it is possible for me to view z as a function of t only. I want to know if I want to view z as a function of t only, what will be dz to dt? So z as a function of time. So it will be z of t will be equal to, if I replace x with t squared, I will have t squared plus t squared times t cubed. And that's t to the power 4 plus t to the power 5. So dz to dt will be derivative of this function respect to t to the power 4 plus t to the power 5. And that's 4t cubed plus 5t to the power 4. So this is one method to find dz to dt. Second approach or a solution to we can find dz to dt using this formula, chain rule above. Let me call it formula star. Using multivariable chain rule. Formula star above. Then we get the dz to dt equals dz to dx. Dx to dt plus dz to dy, dy to dt, dz to dx, derivative of z respect to x. Z is x squared plus xy. Respect to x, the derivative would be 2x plus y. Times dx to dt. Dx to dt, x is t squared. Dx to dt is 2t. Derivative of z respect to y is just x. And dy to dt will be, derivative of y respect to t will be 3t squared. Now if I replace x with y, x with t cube, x was t squared, y is t cube. Then I'll have 2t squared plus t cube times 2t plus t squared times 3t squared. So this will be 2t cubed plus 2t to power 4 plus 3t to power 4. 2t to power 4 plus 3t to power 4, that's 5t to power 4. So 2t cubed plus 5t to power 4. Sorry, 2t squared times 2t squared. 2t squared times 2t is 4t cubed. 4t cubed. 4t cubed plus 5t to power 4, which is same as the answer we got in solution number 1. Same answer as solution 1 above. So one way to find dz to dt is using multivariable chain rule, which can be written this way. Now in our case, back to our problem, we want to find d to dx of this. This is my z here. So instead of t, I have x here. So I have to replace t with x. So back to our problem. We want to find d to dx of f of x and y. In our case, t is x is x, and y is y of x. Remember, in our assumption, x and y were functions of t. X and y were functions of t, the independent variable. Here, the independent variable is x itself. X, of course, is a function of itself because x is equal to x, and y is equal to y of x. Y is a function of x, right? So we can say y is y of x is a function of x, and x, of course, is function of itself because x is x. So our t here is x is still x. So t and x are both x, and y is a function of x because my t is x here. So I can still use this formula, just replace t with x, and x is still x, y is still y. So dz to dt will be equal to, so by formula star above, we can say dz to dx equals df, or in this case, it's capital F, times dx to dx, because my t is x, df to dy, dy to dx. And my z is capital F here. And dx to dx is 1. So I can say d to dx of capital F is equal to df to dx times 1 plus df to dy, dy to dx And this was 0. Remember? When I started with this, d to dx of capital F was 0. So d to dx of capital F, which is this expression, is 0. So what will be the condition now if I compare this, compare with the original equation? Remember, what was the scenario? The scenario was that we wanted to have an equation of this form, and we wanted this guy here to be the solution of this equation. So if we started with this solution, we differentiate respect to x, we got this. But we want this function to be the solution of, this is supposed to be capital F of x and y equals c, must be the solution of m plus n dy to dx equals 0. See, this guy here must be the solution of m plus n dy to dx. So when I say m, I mean m of x and y. And when I say n, I mean n of x and y. Just for abbreviated, to be abbreviated, I just use the m and n. So here, if capital F of x and y equals c is the solution of this guy here, this equation, m plus n dy to dx equals 0, then I can compare this equation with this equation to find my m and n. So comparing m plus n dy to dx equals 0 with df to dx with df to dx plus df to dy, dy to dx equals 0, we can conclude that m must be df to dx and n must be df to dy. So now what will be the conditions on m and n? Now the conditions conditions on m and n can be found through, so now dm to dx, what will be dm, what will be dm to dy? Dm to dy will be d to dy of df to dx. And this will be d squared f to dy to dx. And dn to dx will be d to dx of df to dy. And this is d squared f to dx dy. So dm to dy, partial derivative. Remember, m and n are functions of x and y. So all these, I have to use partial derivatives, because if I have a function of two variables, I have to use the notation of partial derivative to specify that I'm differentiating respect to which variable. Am I differentiating respect to x or respect to y? So partial derivative of m respect to y is second derivative of f respect to yx. and partial derivative n respect to x is again second derivative of f respect to xy. Now, what is the relation between these two derivatives? Both of them are the second partial derivative of f respect to xy. It's the mixed second derivative of f, both of them. These two quantities are equal if the second mixed derivatives are continuous. So this is what you learn in Math 213, basically. So from Math 213, we know these are equal if second partial derivatives are continuous. So under this assumption that second partial derivatives are continuous, we can say that, so we showed that if the equation m plus n dy to dx equals 0, this equation here, has a solution of the form capital F of x and y equals c, then we can say partial derivative of m respect to y is equal to partial derivative of n respect to x. Now, conversely, it can be shown that if m plus n dy to dx equals 0 and partial derivative of m respect to y is equal to partial derivative of n respect to x, then this equation has a solution of the form capital F of x and y equals c. So this works both ways. If this equation has a solution of this form, then this condition holds. So this is what we showed. But it can be shown that the converse is also true, meaning that if you have an equation of this form and if this condition holds, then the equation has a solution of this form. So for this reason, we call an equation of this form with this type of condition, we call it an exact equation. So an equation of the form m plus n dy to dx equals 0 with partial derivative of m respect to y equals partial derivative of n respect to x is called exact. It's called an exact equation. Now, how can you find the solution of an exact equation? So to find the solution of an exact equation, we can integrate, we can start with, let's start with dm, so m equals df to dx. Remember we had this equation before, that m, capital M, is equal to partial derivative of f respect to x. So we can start with df to dx equals m. Then we can integrate both sides. Then integrate both sides. Noting that the constant, because when you integrate both sides, there will be a constant involved. Now that constant could be a function of y, because when you integrate respect to x. When you integrate respect to x means not only constants are considered as constants, but any function of y is also considered as constant. Because when you integrate or you differentiate or integrate with respect to x, that means y is behaved or considered as a constant. So noting that the constant involved after integration is a function of y. Now then we can find this function of y using the other restriction. Next, find this function of y using the other condition, which was n equals df to dy. Now let me show you in an example how we can do this. Example, find the solution of two x y squared plus 4 equals 2 times 3 minus x squared y times y prime, with y of minus 1 equals 8. Now, if you want to apply the method of solving an exact equation, first we need to verify that this equation is exact. Let's see whether we can verify that this equation is exact. So the answer is, first, we will find out whether this equation is exact. So what do we have here? We have 2xy squared plus 4 minus 6 plus 2x squared y prime is dy to dx equals 0. So this is my m, this is my n. Now what can we say that regarding partial derivative of m respect to y and partial derivative of n respect to x? So, all right, dm to dy is d to dy of 2xy squared plus 4. Now, for differentiating respect to y, we have to assume x is a constant, and the derivative of y squared is 2y, and then 2x times 2y will be 4xy. And dn So I think I made a mistake in the sign of this term because I've taken this term to the left-hand side. So 6 becomes minus, but then minus 2x squared y becomes plus 2x squared y. So then d to dx of n will be d to dx of minus 6 plus 2x squared y, and this is also for xy. So that means the equation is exact. And to solve it, let's start with m, which is df to dx, and that is 2xy squared plus 4. Now this is derivative of f respect to x. So if we integrate respect to x, then we can say that capital F of x and y is equal to, now antiderivative of 2xy squared respect to x will be x squared y squared plus 4x plus c of y. So if you remember in the algorithm to solve the equation, we said we start with m equals partial derivative of f respect to x. We integrate both sides respect to x, noting that the constant involved will be a function of y, because when you differentiate or integrate respect to x, y is considered as a constant. So the constant, rather instead of constant, we will have, instead of c, we have c of y, because y is also a constant here. Now to find c of y, we said we have to use the other condition. Use n equals df to dy. So what is n here? N here is minus 6 plus 2x squared y equals d to dy of this function here, x squared y squared plus 4x plus c of y. So that means minus 6 plus 2x squared y equals derivative respect to y of x squared y squared is 2x squared y. Derivative of 4x is 0 respect to y, and derivative of c of y will be c prime of y. Now if I compare two sides by comparing, we can say that minus 6 is equal to c prime of y. And that means if you integrate respect to y, then we will have c of y equals minus 6y plus a constant d. If derivative respect to y is minus 6, the function must be minus 6y plus a constant. Now that we found c of y, if we substitute back, then we get the formula for capital F and for our solution. So the solution will be of the form capital F of x and y equals 0. Why am I saying that capital F of x and y equals 0? Originally, we said capital F of x and y equals a constant. But here I'm saying equals 0. Well, the reason is I already included the constant here. When we said plus d, so I already included the constant. So there is no need to include the constant one more time here. But it doesn't matter, even if you include a constant here, then you can take this constant to the other side and you can call the new constant another name, assign a new letter. So it still doesn't matter whether you say 0 or say another constant, as long as you include the constant here. But if you didn't include the constant here, well, you had to include the constant here instead. So here our solution will be x squared y squared plus 4x minus 6y plus D equals 0, and where D is a constant, and finally to find the constant D, we can use the initial condition. What was the initial condition? The initial condition was y of -1 equals 8. Y of -1 equals 8. So if we replace x with -1 and y with 8, then we get -1 the whole square times squared plus 4 times -1 minus 6 times 8 plus D equals 0. So that gives me 64 minus 4 minus 48 plus D equals 0. And then 64 minus 52, that will be 12 plus D equals 0. That gives me D equals -12. So substitute back. Then we get x squared y squared plus 4x minus 6y minus 12, D is -12, equals 0. So this is the solution for our IVP. The solution of IVP above.